Alright, example 1. We have a gas and it is expanding from 0.87 liters to 2.46 liters in a cylinder under constant external pressure of 1.05. Calculate the work associated with the expansion of this gas. And before we start calculating the work, let's first make sure we understand what the sign would be. The gas is going from a smaller volume to a larger volume. So the gas is expanding. When a gas expands, it is doing work. So if the system is doing the work, that means the work is going out of the system, so the sign is negative. Right? So as we calculate, we'll make sure we have the correct sign. So first off, what is our equation? The equation for work is negative P change in volume. And when we look at the change in volume, we want to make sure that we do the final volume minus the initial to get our sign correct. So here our pressure is 1.05, our final volume is 2.46, and our initial is 0.87. So we'll simply subtract those volumes and multiply by 1.05. Then we have our negative sign out there to make sure that we get our sign on work correct. And it turns out to be negative 1.67 liters times atmospheres. Those units don't really cancel, so we just put them together. Liters times atmospheres. If you wrote atmospheres times liters, that would not be incorrect. Notice the sign again is negative because the gas expanded. Here they show the conversion between liter atmospheres and joules. You see here at the bottom, they show the conversion between liter atmospheres and joules. This is not a conversion that you would be expected to memorize, but 1 liter atmosphere is equal to 101.3 joules. So they just use that as a conversion factor, and they find that negative 169 joules of work were done by the system, and so this would be known as exothermic. If our values are negative, we're giving off energy exothermic. If they're positive, overall the system took in energy, so that would be endothermic. All right, example 2. 1,142 joules of heat are added to a cylinder. Heat is Q. Okay, so they just told us what the Q value was. And the heat is added, so it's coming in. So what should the sign be? Positive. And then the gas expands from 1.35 liters to 4.18 under a pressure of 1.03. Calculate delta E. Now we know that delta E is Q plus W, and Q is given to us, but we need to figure out what W was for this process. If the volume got bigger, which it did here, what should our sign on W be? It goes from 1.35 to 4.18. That means that the system, the gases in the system are expanding, so they're doing the work. So the sign on work should be negative. So let's work through this. So we have work first that we're going to calculate, and that's the pressure times the change in volume, and then we put the negative sign out front to make sure we get our sign correct on work. 1.03 is our pressure, and then we're multiplying that by the difference in our volumes as it expanded. So we find that 2.91 liter times atmospheres of work was done by the system. So we have a negative on our work. Now we'll need to change the work to joules to compare it to the heat so that we can add them together to find delta E. So we multiply that work by that 101.3 joules. That's equal to 1 liter times atmospheres. So that'll convert, and that shows us that it's 295 joules of work were done by the system, so it's negative. We still have that heat, though, that we need to put that with if we're going to find delta E. So we've got Q, which we said should be positive because the heat is coming in, while our work is negative as the system is doing the work of expanding. So altogether, we have a delta E of 847 joules. So that means altogether, there was still more energy coming into the system than going out. The next thing we want to talk about is something called the enthalpy of a reaction. And enthalpy is directly related to heat. So when we talk about the enthalpy of a reaction, we have a different sign. So it's delta H, not Q for heat. But it is the heat released or absorbed in a chemical reaction. The difference between delta H and Q is that delta H is going to be on a per mole basis. Whereas Q, remember, is the total heat of the system. So here we're looking at heat released or absorbed in a chemical reaction, so it's moving, and we're going to talk about it per mole. There are several different ways to find delta H, and we'll work through those in this unit. It's kind of the main focus. So as we move forward, you want to know, how can we find delta H? What are the different ways? Make sure you know the equations and when to apply each one. When we talk about delta H, remember the delta means the change. So we're looking at the change in the heat as a result of the chemical reaction. And that will be the difference between the heat that the products had and the heat that the reactants have. So there's some heat contained within the products and some within the reactants. And what's the difference between those is going to be our delta H, which will be the heat absorbed or released during a chemical reaction. For our signs here, very important, we're going to keep the same kind of sign lingo. If it's positive, that means that heat was absorbed during the reaction, so that would be endothermic. And if delta H turns out to be negative, that means that it is exothermic. Here is an example of an enthalpy change for a specific reaction. And this is the reaction that would be used if you had a hydrogen cell powering your car. A hydrogen cell has been suggested as a good way to power cars because it has less emissions than burning fossil fuels. If you look at the hydrogen fuel reaction that would take place in your car, it would give off, so notice this negative sign here, would give off 572 kilojoules per mole. And the product is water, so that's really safe, right? All we need is some hydrogen and some oxygen. We can power our cars and they'll just give off water. So no horrible gases coming out of our tailpipes. The only problem with that is, where are you going to get the hydrogen gas from? There's some hydrogen gas in the air, but it's a pretty low percentage, and it's definitely not enough to power our cars. So we would have to make hydrogen gas, and one of the best ways to make hydrogen gas is from water. So we would run the opposite reaction, which is what you see down here, to get this hydrogen gas, which we could then put in our cars to run the reverse reaction. The only problem is, to get the hydrogen from the water, you have to put in, notice the sign here is positive, that much energy. So you've got to get the hydrogen out of the water, which requires energy, to then put the hydrogen back into the water, which would give off the energy to run the cars. And so a lot of people's argument is, where is the energy going to come from to get the hydrogen out of the water in the first place? And really the only way we know to do that is to use some other form of energy. That could be wind energy, solar energy, or again, fossil fuels. So we're kind of running back into the same problem. Our cars may be giving off less emissions, but we may be creating more just to get that hydrogen. So if you have any questions about that or want to explore that further, that could be an interesting topic of discussion. The main point here in the chemistry is if you run the reaction backwards, you've got to put in the energy that you get out if you ran it forward. This is a visual kind of showing us that. So up here at the top, we have our reactants, hydrogen and oxygen, that we could have in our hydrogen cells in our car. And as they make the water has less potential energy, see? And so we would get that much energy per mole. However, if we wanted to take that water, which has less potential energy, and produce the hydrogen and oxygen, we would have to go back up the hill, so to speak, and so we would have to put in that much energy, and so that's a positive. So opposite reactions, that's just a flipping of the same process, are going to have the same value for our delta H, but with an opposite sign. There are 4 ways for finding delta H. So in this lesson, we'll focus on the first way, which is using average bond enthalpies. We may have talked about this some when we talked about Lewis structures and the energy inside those bonds. There's 3 other ways to find delta H, and those will be the focus of the next lesson. Recall from when we talked about bonds that when the atoms are far apart, they have a higher potential energy. So I'll keep referring back to this graph. But they have a higher potential energy. And then as they come together, remember it swoops down. And if they get too close, it goes back up again. But down here, when they form the bond, they have a low potential energy. So the potential energy goes down as the electrons from one approach the nucleus from the other. So the electrons' energy decreases as they get close to the nucleus of the other atom. And depending on how much that energy decreases, that's our bond energy. So if it decreases a lot, then we'll have a large bond energy. If it doesn't decrease as much, then we'll have a smaller bond energy. So bond energy or bond enthalpy is the energy that is released during the formation of a bond, because that potential energy is getting lower as they come closer together. However, that same amount of energy would be needed if we wanted to break that bond apart. So bond enthalpy or bond energy is the energy released when the bond is formed or the energy required when the bond is broken. So because it's released when it's formed, that's going to be a negative sign for our enthalpy. But if we're breaking the bond, that's going to be a positive sign because we've got to put energy in to do that. So how do we calculate delta H using bond energy or bond enthalpy? The equation will be delta H equals the sum, that's what this sigma is representing here, the sum of all the bonds that are broken minus the sum of all the bonds that are formed. The reason we have a negative here is because when we form bonds, it releases energy, and that's exothermic. So that's why the negative sign is there. And when we break bonds, that requires energy. So all of these are going to be positive. When we have BE in this equation, that's just referring to our bond energy or bond enthalpy, and that'll be bond or released when the bond is formed. Okay, so positive when the bond is broken, negative when the bond is formed. These graphs you'll see a lot, and they're very helpful for our understanding here. This is called an energy diagram for a reaction. So here we start off with our reactants, and let's say this reaction is AA plus B yields AB plus A. So here's the only bond that we have is this AA bond. So we've got to break it. In order to break it, you got to put in energy. So you got to go up the hill. So you got a positive change here. Now we have our bonds broken, and now we're ready to form this AB bond. When you form a bond, you release energy. So you're going back down the hill, negative. Depending on which one's greater, the breaking or the making of the bonds, the overall will be endothermic or exothermic. In this example, we're getting more energy when we make the bond. So overall, we got more energy than we put in. So overall, this change would be negative for our delta H. If the process is exothermic, which is what we just saw in that example, then more energy is released. And when is the energy released? When we form the bonds, then is required to break the bonds. Sorry about all that underlining. My computer's going crazy. Notice the key language here, and that's what I want you to be picking up on, though. The energy is released when the bonds are formed, and those formed are in the products. There is energy required to break the bonds, and those bonds are in the reactants. If it is exothermic overall, though, that means we had more energy released than we did required. Let's look at the opposite scenario. If we have an endothermic reaction, that means that less energy was released than was required. So we required more than we released. When is it released? When the bonds are formed in the products. When is it required? When the bonds are broken in the reactants. So if it's endothermic, then our reactant bonds must be stronger. So that means the products are at a higher potential energy. So that graph would look like this. We break the bonds, and then when we make them, we don't get that much energy out. So the products are at a higher potential energy. We had to put in a lot, positive, we didn't get much out, negative. All right, let's look at the actual calculation here using the following reaction. This is the reaction for the combustion of methane. So we have CH4 and 2 molecules of O2. These are the things that we've got to break apart. And then in the products, we've got 1 carbon dioxide molecule and 2 waters. These are the things that we're going to form. So for our calculation, it's going to be all of these bonds minus all of the product bonds. So bonds broken minus bonds formed. Right, so here we have the layout. In that CH4, we've got 4 carbon-hydrogen bonds. So here we have 4 times the energy in those bonds. Here we have 2 O2 molecules. And if you can recall, an O2 molecule has a double bond. So we have 2 times the bond energy for that bond. Those are going to be added together. Then we're going to subtract the products because they're being formed, so that would be exothermic. In CO2, you can recall, there are 2 carbon-oxygen double bonds. So 2 times the bond energy of that. And then in water, you have 2 bonds, 2 OH bonds. But if you look, we have 2 water molecules. So if there's 2 bonds in each one, and there's 2 molecules, that's 4 of those bonds. Right? So we have our bonds broken minus all of our bonds formed. So we'll plug in those numbers from the table and then solve, and we find that overall we have a delta H value of negative 824 kilojoules per mole. And this negative sign tells me what? It tells me that it's exothermic, that it's giving off heat. It also tells me that my bonds that are formed were stronger than my bonds that were broken, that this part that I subtracted was bigger than the bonds that I broke. And it tells me that if I look at the chart, it would look like this. I broke some bonds, and then when I made them, I got more energy out. So these reactants are at a higher potential energy than my products. My products are at a lower potential energy, which means they have stronger bonds. Right, another example, here we have hydrogen and oxygen making water. And we already know from previous example what the delta H value is. The question, though, is what is the bond energy or a hydrogen-hydrogen bond, which is missing from this table. They really like this question on the AP exam. They'll give you the delta H value for the whole reaction, but they want to know what is this missing piece, this missing bond energy. Right? So if we have bond energy values, we're going to be using the equation delta H equals bonds broken minus bonds formed. Then we'll go through our reaction and figure out what bonds we have. So in the reactants, those are the ones that we're breaking, we have 2 hydrogen molecules. So that's just 2 HH bonds. And then we only have 1 oxygen here, so that's 1 oxygen double bond. In water, remember there's 2 bonds, but we have 2 water molecules, so that's 4 of those bonds. Notice the negative, because water is a product, and those bonds are going to be formed, not broken. Right, then we'll plug in what we know. In this case, we know our delta H value, but we don't know this value here. So what they did is they rearranged the equation. They moved delta H over there, and then we have this moved over here, and then they kind of flipped their signs. Okay, you could do it that way, or you could just plug your numbers in and solve for your variable. Important to note here, though, is you have 2 of these HH bonds. And that's what we're looking for. All right, so then we'll plug in our values for delta H and for the other 2 bonds that we know, and we come up with 801 kilojoules per mole. But we've got to divide by 2, because there's a 2 over here in front of this bond energy for HH. So then we find that the bond energy is 401 kilojoules per mole. When you're solving for bond energy or bond enthalpy, it should always be positive, because it should represent when the bond is broken. If the bond is formed, it'll have a negative sign in the equation, but your answer for bond enthalpy should always turn out to be positive. So if it doesn't, go back and check your work. Because when we say bond enthalpy, we're saying the energy required to break the bond. So if the bond is formed, of course we have to put a negative sign in front of it in our equation. But in the table, if we look back, when we're looking at bond energies in a table, the values are always positive. So keep that in mind if you're ever solving for one of those unknowns. Alright, so that's it for bond enthalpy. You can use those values to calculate the overall delta H, or if you have the delta H value for the reaction, you can use that to find a missing component in your bond enthalpy.